So first start with two functions, f that has a domain, this is again the domain a, so it's a real function. For any value x in the domain, it gets a value y, that's a real number that comes with the rule f of x, and then g with a domain b, so to each number b it assigns x in b, it assigns a number g of x. Okay, so now with the two different functions, what we can do is we can do some operations with them. The first one is to sum them, the addition of to sum. And then we can define a new function, the sum function, f plus g, which is defined in C, which is the intersection of A and B. Okay, so if A is this domain and B is this domain, then C is this. Okay, it's just the set where the two other sets overlap. Okay, and that makes sense because that's the only point where both f and g are defined at the same time, right? If you want to do f plus g, but are taking values of f where g cannot function, then that doesn't make sense to sum them. So the sum is only defined in the intersection between the two domains. Okay, and the rule is just to sum the mapping of the two functions. Okay, so if to x you assign f of x, to with g you assign g of x, the sum is just the sum of the two assignments. Okay, so for instance, you have f is x and g is x squared, then f plus g of x, so the new function is x plus x squared. Okay, so you can see how all polynomials arise from this kind of combination. Okay, now the product is similar. Okay, now again it has to be defined in C, where C is the overlap of both domains. So the product function f times g is just the product of f of x times g of x. Okay, so again x squared is just g is just x times x. Okay, you see, that's how we define higher order polynomials actually. Okay, and then finally the quotient. Now here the domain is a bit different because if you have f and g and then you're going to divide f over g, as we have seen before, it doesn't make sense to divide anything by 0. So b prime here is b, but without the values of x that make g of x be 0. Okay, so it's the values of x that belong to b such that when they are mapped by g are not 0. Okay, so it's b without the values of x that are mapped to 0. Okay, now once we have that, then the quotient is just, as you would expect, the division of the two values of the function. Okay, now the next operation that we can think of is what we call composition. Okay, and it's written by this circle here. Okay, it's f composed with g, okay, over f of g, and then so again from the domain C, so it well, no, sorry, yeah, I'm going to talk about C right in a minute. So to any number C, the composition applies is f of g of x. Okay, so if we start in x, then you apply g, and then you have g of x, and then you apply f, and you get f of g of x. You see? So it's like these two steps in the process. Okay. Now, okay. So remember that g, the domain of f is a, and the domain of g is b, right? Now, what's the domain of f composed with g? What's c? Okay, what's c? Now, in order for let's see, for f of g of x to exist, then g of x has to belong to a, right? And x has to belong to b, right? So So okay, so C is a subset of B, that's for sure. But now it includes only those values in B such that when they're mapped by G, they belong to A. Okay? So in other words, we write it like this. C is the set of values of X that belong to B such that G of X belongs to A. Okay? That's C. Okay, that's the definition of the domain of the composition. But it's not easy to find it in examples, okay? Or well, not easy to get a general rule of how it is, okay? So let me give you an example of this. So suppose we have f of x is 1 over x minus 1, and g of x is the sine of x, okay? So a, which is the domain of f of x, is, this is a rational function, so it's the reals except the zeros of the denominator. The zeros of the denominator here is just 1, okay? So it's the reals except 1. And the domain of b is the reals, right? The domain of the sine is the reals. So it's simple, okay? Now if we composed f with g of x, then what we get is 1 over sine of x minus 1, right? So you have to do f of g of x, okay? So f, and instead of x you write g of x here, okay? Now the domain of this function is the reals except the points that make this be 0, but the zeros of this is where the sine of x are 1, and this is pi over 2, 3 pi over 2, 5 pi over 2, and so on, right? So it's the odd multiples of pi over 2. So this is, C is just the reals except, and then 2n plus 1/2 of pi, okay? So you can write it like in different terms, but this is one way. So, and n is an integer number, okay? So this is just the multiples of pi that give you this kind of numbers, okay? So this set is not, well, it's not complicated, but it's just a line with a lot of holes, right? And it's not obvious that starting with this kind of domains, you would get a domain like this with a composition, right? So bear that in mind when we study compositions. And let's see, well, yeah, so the composition is not commutative, okay? So f of g is not the same than g of f in general. So g of f here, in this case, using this example again, would be the sine of 1 over x minus 1, which is a very different function, as you can see, okay? But it's a property of the compositions is that it is associative. So f of h of g is the same as f of h of g. Sorry. Okay, f composed with h with g. Okay, so we can write it like this without the parentheses to make it easier, right?